Hi, my name is Patrick, and together with Sandhya, we work at Hyperloop One. We will present today how did we manage to scale our simulations and analytics for the purpose of generative Hyperloop design. So let's jump into the agenda of our presentation today. We will first tell you what are we doing at Hyperloop One and what is our subgroup, Machine Intelligence and Analytics, doing. We will then show you an example of our simulation and what are the design challenges of building a data pipeline for running hundreds of these simulations in the cloud. We're going to show you which were the tools we use, short demos of these tools, followed by a demo of sample simulation run with our pipeline. Then we'll quickly jump into one of the conclusions that we discovered using that pipeline that is related to demand modeling. So we, Hyperloop One, are a startup with around 250 employees in downtown Los Angeles, and we are building a new transportation system that is based on a vacuum tube and small passenger or cargo vehicles that we call pods. It offers zero direct emissions because we are using electromagnetic levitation and propulsion, and because of that, we can provide very short travel times, but not only because of that. We are also on demand. So imagine ordering your Hyperloop ride using the web or phone app. We run hundreds of tests at scale and have a 500-meter test track in the Nevada desert, and we are constantly planning and building new tests and enhancements, so please follow us to see how Hyperloop is becoming a reality and learn about the future of transportation we are building for you. So with this new transportation system, people are asking a lot of questions about safety, cost, what is the real travel time, and many, many other. And our group, Machine Intelligence and Analytics, is doing operation research for Hyperloop. We are providing analytics products for our engineers and business teams so that they can show governments, partners, and investors that Hyperloop is the solution they are looking for. For example, we compare Hyperloop with high-speed rail, airplanes, and other modes of transport. We are answering all these questions using simulation and internal and external data. For example, we could answer the question, what is the optimal vehicle capacity for a given geography? And how many passengers can we realistically handle in a given scenario? And again, we answer all these questions using data. So our sample data flow would be to gather demand where people want to travel for a given geography, then fit route alignment in the land using our 3D alignment optimizer and geospatial data. Then we schedule the trips for the passengers using that demand and Hyperloop alignment and run the simulation. After the simulation, we then compute performance and cost metrics, and usually we discover something could be improved. For example, maybe we can sweep some more parameters. So over time, we run more and more simulations for more and more parameter sweeps. And after a few weeks of running, we have a bunch of answers to the questions asked. So I mentioned running the simulation. We call our simulation software SimLoop, and it's an agent-based, high-fidelity transportation system simulation that we develop in-house. It can simulate the Hyperloop alignment pod, which is the vehicle, the physical behavior of the pod, control systems, interactions with the outside world, as well as passengers and Hyperloop stations that we call portals. So let's take a short tour in our simulation software, after which Sandhya will tell you more about the pipeline.
Hi, I'm Sandhya. So we just now saw the Hyperloop simulation video. Now I'll walk you through the flow of the Hyperloop simulation. So we first start by capturing the demand and ridership patterns of the existing route in consideration. And then we do ML models to predict the future demand. And with that demand data, we send it into a trip scheduler, which will then do the pod allocation and departure schedule for us. We also have a track optimizer, which gets the possible optimized alignment for the route in consideration based on the geography and cost. We have additional sweep parameters as well, like say, for example, allowing whether ridership is, whether we can ride in parallel or ride sharing is allowed. And those all are fed into a simulation software, which then yields the simulation for us, which we just saw. Those simulation results are then analyzed to give us some metrics to answer the business questions. So imagine doing this again and again for different set of parameters, different set of alignments and files. And we have to make sure that our analytics platform is able to handle this volume and is robust enough to run this again and again. So why we need to be flexible and why do we need to be fast? So we need to have accurate answers and we need to have them right now as soon as possible. So we need to have it flexible and fast. And we have data volume changes occurring based on different alignments and different use cases in our environment. And also we are going to get, we are getting data from multiple engineering teams in different file formats and different processes. So we have multiple data sources. And also see, we have to add new applications to our system, say pricing model prediction. It has to be seamless enough. And being one of the kind technologies, and we have to keep up with the latest of all the technology and tools, we might need to migrate between toolsets and platforms. So for all these reasons, we need our platform to be flexible and fast. So this is not something new to set up such a robust and dynamic platform. So a lot of big companies like Google and Uber have already shown us the way. Precisely, they adopt the cloud technologies. They ensure there is microservice architecture for flexibility. They use distributed computing to be fast enough. They are also auto-scalable to meet the large demands. And they use the Lambda Kappa architecture to be dynamic as possible. In order to implement those architecture guidelines, we have a lot of challenges being a startup. So the first challenge is that we have resource constraints, specifically with development maintenance. We also have limited DevOps support in order to support such a platform. And in addition, being one of a kind technology, we need to have security implementations in place as well. And lastly, we need to have traceability and governance in our platform so that the quality of our product is ensured, because we are directly leading the passengers. So this is our analytics platform tech stack. We have a couple of tools, primarily open source tools, which help us with our tech stack. NiFi is a data flow manager, which helps us very much in place with the flexibility and microservice architecture. Parquet is a data format for columnar and using it for huge demand and huge growing demand of data. Spark is our compute engine, which is open source, but we are using the Databricks platform so as to ease us with the DevOps and the other limitations which we had. And we use MLflow for our analysis. So in all these, in addition to all these, we also use other like cloud-based technologies like Docker, Amazon's EC2 and S3, and Kubernetes as well. These all make a very flexible and nice stable platform for us. So this is our overall architecture of an analytics platform. So as you can see on the left-hand side, we have a couple of files which come as input, specifically, say, for the velocity profiles or the portal models and vehicle models, etc. The information and the relationship between these files are persisted on our database. And we also have an additional configuration application, which our users use for primarily picking and choosing the different files for the simulation to run. Once they hit the run, the NiFi takes control. It does some transformation, cleanses the files, and runs the simulations on our EC2 engines in parallel. And once the simulations are completed, the control comes back to NiFi and is then given to Spark for our analysis job. Once the analysis jobs are complete, the results are stored as experiments on MLflow, and we use MLflow to analyze the different batch run results and compare them and see what questions we have answered and how much of it is gives us the information, and we have a report of it. So this is our overall flow. So now my colleague Patrick, he will explain about how we use Spark and Databricks in our platform.
So let me tell you our Hyperloop data story. About a year ago, our data sizes started to grow from megabytes to gigabytes, and our processing time started to go from minutes to hours. And our Python scripts, especially Panda scripts, were running out of memory. And so we decided we need more enterprise and scalable approach to handling our data. And we tried different solutions, and obviously we found that Spark and its family is the facto standard solution, and it's great with so many connectors and tools around. So we decided we are going to have a bunch of Spark workers and drivers and Hadoop file system and S3 mounted in that file system. This is already a big infrastructure, so we already knew we don't have enough DevOps to manage that, and this is why we are using Databricks. But then we also realized that our previous code was coded in Pandas, and to use it with Spark, we would have to use either PySpark or Scala. And we, and particularly me, since I would have to do it, weren't particularly happy about that, since we would have to rewrite all thousands of lines of code in Pandas. And we weren't experts in PySpark or Scala. And this is where Koala's package comes in. Exactly when we needed it, more or less one year ago, around April, Databricks open sourced Koala's package that is doing exactly what we needed. So it's translating our Pandas API into PySpark so we can scale our Pandas code very easily with the familiar Pandas API. So now let's talk about another part of our system, which is called MLflow. We use it to log, track, and analyze our simulation runs and results. So for those of you who don't know, MLflow is an open source tool that allows you to log machine learning models, its parameters, and metrics. So for example, here, using this UI, if you run a bunch of models and log them, you can see the parameters and metrics for all of them, and then select the best model. Then you can deploy it to production using MLflow projects and models on the top right on the slide. But in this presentation, we are particularly interested in MLflow tracking. So let's talk about it more. We found that MLflow tracking serves its purpose very well also beyond machine learning. Our simulation runs are also expecting a lot of input parameters that we can sweep, and also have a lot of outputs that we score to create numerical metrics. Instead of developing our own solution to track, query, and analyze simulation runs, we use MLflow tracking as a generic experiment logging and visualization tool. We just treat every simulation as an experiment and log it as such. And we found it super convenient and very cost effective. We actually saved so much time by not having to develop the simulation tracking tool ourselves. And it integrates very well with external tools for APIs. For example, there is an API to query and export experiments to Pandas data frame that we use a lot. And we found that MLflow serves its purpose very well for tracking our simulation. And our simulation actually contained a lot of AI algorithms. So instead of MLflow, we actually call it AI Flow. Now I will let my colleague Sandhya explain NiFi, our data integration and pipelining tool.
So Apache NiFi. NiFi is a powerful data flow manager. And for any data-driven analytics, you need to have a very good data flow. So it is data agnostic. NiFi also supports transformations and data routing. It has 250 plus inbuilt components. It also has a minify and a NiFi registry extensible with it. And so, for example, now say if you want to merge two JSON files, which have the same file pattern, and perform transformations and put them in S3. So first you go and choose the get file component. You give the parameters of the file and the pattern you want to pick. And then you can use the merge file component, merge content component to give the header and the footer information and how you want to merge the two files. You can also, in the connector between the two components, you can see that you can do prioritizations and buffering mechanisms. And in addition, for each component, as you can see, we can also have scheduling mechanisms, like you can put the schedule in them. And you can use the Jolt transformation component for putting the transformations and add S3 attributes, and also use the put file component along with the AWS credentials as controller services. Now, if I want to run, I can pick and choose and run whichever component I want to. So I have just run the first component here, and I can see that the files which are picked are queued in the flow, and I will be able to see the different flow content and the flow attributes which are related for that particular file. Once I confirm, I can choose to run the remaining part of the flow as well. And after the flow has completed, I will be able to see the provenance of the particular, whether the file has been put in S3 or not, and whether it was successful, and what was the content of the file which we just put. So this is the complete flow. So Apache NiFi is also good at real-time command and control. Say, for example, if you want to set up the concurrency control. So for a particular component, you want to set up whether the task needs to be concurrent and how concurrent it needs to be, and whether execution needs to be running on all nodes, etc., and the schedule needs to be arranged as well. You can also set up whether the queue prioritizations, like whether it has to be first in, first out, and buffer, and etc. In addition, you can also add control services for external connectors, like say Postgres or AWS. And on top of all this, NiFi also gives the power to set up good data security using SSO or SSL, basically. The most important feature of NiFi is power of provenance. It gives inbuilt provenance, and we need provenance and lineage for efficient traceability in our analytics platform. So in this screenshot, as you can see, it's a screenshot of a put file components provenance event, and these are the details of that provenance event. And on the right-hand side, you can see a tree-like icon. When you click it, you will be able to see the complete lineage of that particular provenance event. So each and every circle here is a component's provenance data. And once you click any one of the circles, you will be able to see the detailed description of what was that event, what was the flow file, its byte size, and what were the attributes of that particular flow file. And in addition, you'll also be able to see the content, like whether like it's the input or output of that flow file connection. And you'll also be able to replay that provenance event if you need to check if anything is going wrong. This helps with good traceability for us. We just saw all the different components that are used as a part of our pipeline. So we would like to show you a small demo of our complete pipeline. And we would first start by showing you the configurator application, which a user uses to pick and choose the files. Then we will show how the control is transferred to NiFi. And then we will also show how it is simulation is executed in parallel, and how we use MLflow to analyze the results. So first, we'll start off with the configuration application, where the user pick and chooses the files. As you can see, this is our configurator window. You can use the add button to add a particular batch and pick the alignment for that particular batch. And based on the executables available, you can select each of the executables, whichever you want to run. And then when you hit view dependency, you'll be able to see the dependency between the executables and what are the files needed for it. So when you accept that, you will be able to pick and choose the different files, whichever is available for that particular file sets. And as you can see, you can be able to choose the different files. You can also see in the tabs, on the top of the tabs, some numbers coming up. Those are the numbers of the different scenarios which are going to be executed as a part of these file choices which you are making. So if you choose different set of files, the combination yields more scenarios. And as you can see, you can also sweep different parameters. And the more parameters you choose, those also contribute to different combinations of scenarios which you wanted. So when you hit run, you will be able to see the total number of scenarios calculated. And when you hit here again, you will see that the successful batch has been created. So once this batch has been created, the control then transfers to NiFi. So now we will see how NiFi picks up the control seamlessly from after the batch is created, and how the flow progresses. This is a sample flow which we have. And once the NiFi control is passed over here, you would be able to see the data flowing through, and you can see the provenance of the data which is coming in. You'll be able to monitor and view the content of the data. For example, this is a view content. And you will also be able to replay the content in order to see whether if you have any bugs or anything. And as you can see here in the screen, there are multiple simulations running on EC2, all kicked off by NiFi. So once it is kicked off, you can also check what yielded to that particular execution by checking in the details of that particular flow file content, the attributes and the content. And also the best part to see is the provenance, lineage. You can see that where the specific command came from and what all are the files which yielded for that particular command to execute and how the simulations executed. So this is our cloud flow, basically. So once the simulation is executed and our analysis metrics job is running on Spark, all the results are saved on MLflow as experiments, and Patrick will explain about it.
So thanks, Sandhya. Now I'll talk about MLflow, our metrics listing and analytics platform. So as you can see here, this is MLflow window, and every row is a simulation run. And for every simulation run, we have some metrics and parameters. And if we click on the row, we can drill down into a single simulation run. We can, again, for the simulation, see parameters and metrics for that simulation. But the cool part is for every simulation, we compute a bunch of artifacts. Like for this simulation, for example, I created the demand scatter plot, and it's very interactive. Here in the window, you can explore, you can interact with the interactive plotly plot, as well as I created here a histogram of the trip times. So, for example, here you can explore that between different cities, that the trip times are different for passengers. But then what if you want to compare a bunch of experiments? So to compare a bunch of simulations, we select all of this and click compare. And again, here we have a big table where each column is a simulation run, and we see parameters and metrics. But here we also have a way of exploring that data. So if we select the sample parameter and sample metrics, we can see which simulation is the best. And we can also see a contour plot, like 3D plot. So you can see two parameters and one metrics. And here we can see one of these two simulations maybe performed the best. So this would be our further exploration. So I hope you enjoyed our pipeline run for our simulation. And now I would like to share one of the conclusions we drew using this pipeline. As I told you before, Hyperloop is on demand. And because it's on demand, we found that we can provide increased efficiency and passenger convenience. But there is one particular challenge with the on-demandness of Hyperloop that I would like to discuss and analyze with you. So the challenge is we would like to predict areas of high or low demand so that we can redistribute our vehicles ahead of time from the areas of low demand to the areas of high demand. Imagine Hyperloop network like in the picture on the bottom left. If there's a high demand in the center, we would like to redistribute the vehicles so that they are able to pick up passengers right when they need to. And for that purpose, we feed the demand prediction model to our simulation. And we trained these models using historical demand data we gathered for our analysis. And we trained multiple models using Keras, LSTM, and GRU. And actually, we trained it using Horovod in Spark. And we also ran ARIMA and profit models and swept the input parameters to these models using Spark UDF as distributed sweeps. This is a rough example of one of our models. And the blue line you can see shows a ground truth for the demand for a given origin-destination pair. And the model prediction is shown with a green line, and the prediction history is shown with the red line. And this model is trying to predict hourly demand for 3 days in advance for a single origin-destination pair. So as a conclusion from that analysis, the best model we fed into our simulations using the pipeline was able to improve the number of required vehicles and cost by even up to 70%. And this is a really great finding. We also found that sometimes simpler models like ARIMA or Profit sometimes outperform Keras. And additionally, to improve the models, we correlated the weather data and the surrounding event data from PredictHQ with the transportation demand. And we definitely found a correlation that provided a great improvement to our demand models. As a general conclusion, I hope you learned a lot about our Hyperloop project. And I hope you can see we are doing really cool stuff. And by the way, we are still hiring, so please check out our careers page. Our story with Databricks is an amazing partnership, but also a very lucky coincidence with Koalas. And that's a great company. We love using their tools. We also showed you the design of our system that is running and analyzing hundreds of data-heavy experiments. And how did we achieve it with minimal development effort? And we actually coded this platform with 2 to 3 people in 6 months. And here I'd like to give a shout out to our front-end engineer, Justin. He's great. He really helped us figure all this out. And it's actually the integration between the tools that took the most time. And the tools that did the job for us were Knifewise, Spark, MLflow, and Parquet. If you want to learn more about Hyperloop is reinventing transportation, feel free to reach us on Twitter using this handle. And I believe now it's the time for questions.